Hello guys and welcome to this lesson 6b of periodic functions. In this lesson, we focus on graphing periodic functions. In lesson 6a, we look at the periods, the amplitudes and shifts of periodic functions, and here we are looking at graphing these functions. Please make sure you watch this lesson to the end and leave your comments. Don't forget to click on the subscription button below so that whenever we upload any new lesson, you will be the first to be notified. Stay tuned and welcome. So we start with this first example. We have the function f of all x equals that, and we have to sketch the graph of this periodic function. This is the function we saw in the previous lesson. So we have to sketch the graph of this function. We have values from 0 to 2. So we can make a table of values. So f of 0 is equal to 9 minus 0 squared in this interval. That gives us 9. F of 1 is still in the first interval. That will give us 8. F of 2, the first interval, gives us 5. We are still going to look for f of 2 in the second interval because we are not sure if this value is going to be the same. Let's look. If the values are the same, then we are going to do exactly that. So this actually gives us 3 times 2, which is 6 minus 1, 5. So the values are the same. Then f of 4 gives us 3 into 4 minus 1, which is 11. So we now have to sketch these values since we already have a curve here right now. And so this will be giving us, so we calibrate the axis, x axis and y axis. The values, we write them down. 2, 4, 6, 8, 10, 12 on this axis. On the x-axis, we have 2, 4, 6, 8, 10, 12, and -2, -4. Okay, now we start with this first point where x is equal to 0. When x equals 0, y is equal to 9. Now we indicate these points, but we do not shade the circle because this boundary is not included. That's what we explained in the previous lesson. The boundary is not included, so we do not shade this circle. Now when x is equal to 1, we have y to be equal to 8, and when x is 2, we have 5 for this first function. For the second function, normally this is a part of a quadratic 9 minus x squared. We link these points and we have a curve like that. Now for this second part of the function where we have when x equals 2, y equals 5, and when x equals 4, y equals 11. So we just continue, and this second part is a line. So we link this as a straight line, right? So we have actually sketched the curve of this periodic function. We have sketched the curve of this function. So the question that may arise now is, what if they ask us to sketch, for example, they ask us to sketch this curve from x equals 0 to x equals 8. What do? We just copy and paste the various intervals. So we just copy and paste. So this function from 0 to 4 will be the same function from 4 to 8. So we just copy this function and paste again. So we just copy and paste, as you can see. We have just copied and pasted. What if they ask us to sketch from this same value of 0 to, for example, let's say to 11. To 11, we still copy again and paste because from 8, we have an interval that stops. From 8 to 11, we copy and paste. But now, copy and pasting, I will not continue. When I get to 11, I will not continue because they say I should stop at 11. Can you see? Here, the value of x is equal to 11. So that's why I end here. If it was up to 12, I will continue, and this value also be at this other point here. So if I was to end at 12, I'll end here, but I'm to end at 11. So this part is erased or does not appear. So we end at this point here. What if they ask us to equally sketch to, let me say, from -3 to 11? So I'm just taking some intervals and extending. So now I already have from 0 to 11. I just need from -3 to 11. So I'm just going to copy and paste. But since I'm going backwards, I'm going to start copying from this point. I'll start copying from this point, as you can see. and copy it, this function backwards. So as you can see, that's a point. Start copying from here. Then I end at -3. I could have ended at -4. -4, but they said I should end at -3. So I'll not continue to this point. I'll just end around here. So I've completely sketched the curve of this function. And take note, this is very, very important in integration, because at times they may ask you to integrate from a particular value to another value, and you need the knowledge of all of this. Let's take another example. So we have this function g of x defined as x squared plus 1 from -2 to 1 and 1 to 4. And I want us to sketch this periodic function. So to sketch, looking at the first part of the function, when x equals to -2, we see to have -2 squared plus 1, which is 5. When x is -1, -1 squared plus 1, which is 2. When x equals to 0, 0 squared plus 1 is 1. And when x equal to 1, 1 squared plus 1, which is 2. Now, the definition continues from the second part of the function from 1 to 4. So we use the second function. G of 1 will be absolute value of 1 minus 3. 1 minus 3 is -2. Absolute value of -2 is +2. Then G of 2 will be 2 minus 3. So we have 2 minus 3, and absolute value of 2 minus 3 is 1. G of 3 will be 3 minus 3. Absolute value of 3 minus 3 is 0. And the absolute value of 4 minus 3 is equal to 1. So now we can now sketch these points on a graph. We calibrate the graph, and yeah, 2, 4, 6, 8, 10, or that 12. So the first point is when x is equal to -2 and y is 5. So we have -2 and 5. And at this -2 and 5, you can start there's an equal to sign included here, right? That's why I have shaded this circle here, it's included. So you have shaded at -1 and 2, these points. And then you have 0 and 1. We have 0 and 1. And since this is a quadratic, we continue, we have 1 and 2. All right, we have when x is 1, y is 2. But the 2 is not included in this definition. Can you see? When x equals 1 is not included. That's why this circle is not shaded. And we know that equal that this is part of a quadratic curve. So we link these points as follows. That's a quadratic. And then we continue now with this absolute value function from 1. So when x is equal to 1, we have 2. So I have a dot now here because the boundary is included. That's why this dot is shaded inside. Can you see? So this is what you will normally do. That dot is shaded. And then since this is a line, no, since it's a line actually, but it has absolute values. So we have to work with the absolute values. When x is equal to 2, we have the point 1. When x is equal to 3, 3, we have 0. So we have this point. When x is equal to 4, 4 minus 3 is 1. Goes back upwards. This is what we have. But at x equals 4, this boundary is not included. So we do not shade the circle here. So we now link these points because it's made up of a set of lines. And we can now copy and paste multiples of this curve or periods to extend to various intervals. For example, if you have to sketch, let me say we want to extend, we just copy and paste like this. Maybe you have to sketch from this to 7. This is what will happen to 7. What if you have to continue from this point 7 to 8? All right, this question says if you sketch this function from -5 to 8. All right, so we are ending at 8 here. That's why this 8 has ended. But now here we have from we have ended at -2 on the left hand side. We have to move from -2 to 5. So we copy from the end, start copying from the end of this, which is this line or this V set of line. So we copy from that end to this point. And we have now sketched this function from -5 to 8. If you don't understand any concepts, you can watch this severally, or leave your comments in the link below. Or you can equally get to us on WhatsApp directly by getting to the blog, and any concepts can be clarified. So remark, take notes in integration. Take note about such functions in integration. It's always good to make a simple sketch in integration if you are not sure So you carry out that integral. Example number 3, we have the function g of x equals that, and we have to sketch. So you can start from g of 0. G of 0 will be equal to 0 squared, which is 0. G of 1 will be equal to 1 squared, which is 1. For g of 2, so g of 1, we use these two functions to have the same value. So I'll just write g of 1 once. For g of 2, you must use the second sub part of the function. That will give us 2 into 2 minus 1. That's 3. For g of 3, we have 2 into 3 is 6 minus 1, 5. So we have 5. And the second function, look, 7 minus 3 is not going to give us 5. This is the point we have emphasized on from the beginning. That when you have these sub-intervals, you have to take at this boundary and at this boundary. If you look at the case of 1, the values were the same. 1 squared is 1. And here, 2 times 1 minus 1 is 1. But for the value of 3, the values are different. You obtain different values of y, so you must always be very careful with this. It therefore means that if you look at g of 3 using this second function, g of 3 using the third function, part of the function, the values are not the same. With this type of points, you say the function is discontinuous at this point. We will look at discontinuity in the next chapter, that's chapter 7, on limits and continuity. So in looking at limits and continuity, we will also be discussing discontinuity. Now for 4, g of 4 will be equal to 7 minus 4, which is 3. And g of 5 will be equal to 7 minus 5, which is 2. So we have everything set. We now go to our xy plane. We can start with the first point, g of 0 is 0, and the 0 is included in the definition. So that's why it's shaded. 1 is not included in the first part of this function. Then the second part, this subfunction, the second part, since a line, you can just take the first the 2 points is line. You just take at 1 and at 3 and we link the points. And then the last one is equally a line, but the function is discontinuous with this line. So we take at 3 and at 5. At the point 3, we have 4, and at the point 5, we have 2, right? So this is the graph or the curve of this function. And from this graph, you can clearly see that at the value of x equals 3, this function is not continuous. But at 1, it is continuous because the values are the same. So we can copy and paste multiples of these intervals or this period to sketch this function at other given intervals. All right, consider this function f of x equals sine 4x. Take the amplitude and the period and sketch from 0 to pi on the same axis. Sketch the curve of g of x equals 2 plus sine 4x. So the function here is the function f of x equals sine 4x. And they want us to sketch this function from 0 to pi. You can select values from 0 to pi. Normally, with this function, known as the periodic function, you can equally sketch by looking for the period, first of all, and then we copy and paste multiples of that period. So here, the amplitude here is equal to 2 pi on 4, recall. Because we have sine 4x, 2 pi divided by equation of x, so 2 pi divided by 4, that gives us pi on 2. That's the period of the function. Note, when you're working with these functions, we use pi, that's radians, not degrees, unless otherwise they specify. At advanced level, we work with radians. So to sketch this, we are going to look at the period. The period is pi on 2, right? Let's sketch so that you have about 5 or 6 values or more. 5, 6, 7, 8 values are okay. So if you take multiples of 15 degrees, for example, to 90, you can have 6 or 7 values, right? And that would be something very good. So we can have x, we take multiples of 15 degrees. 15 degrees in radians is pi on 12. So 15 degrees in radians is pi on 12. So we have 0, pi on 12, pi on 6, pi on 4, and then pi on 3. The values are increasing, right? 5 pi's on 12, that's 75 degrees, and pi on 2, which is 90 degrees. Now, when x is equal to 0, what is sine 4 times 0? 4 times 0 is 0, right? Sine 0 is 0. So f of x will be 0. When x equals pi on 12, 4 times pi on 12 is pi on 3. And sine pi on 3, that's sine 60, 0.866. I'm approximating here to 1 decimal place for simplicity. Then when x equals pi on 6, 4 times pi on 6 is 2 pi on 3. 2 pi on 3. And that gives us 120. The sine of 120 is equal to 0.866, which is approximately 0.9. When x equals pi on 4, 4 times pi on 4 is pi, right? Sine pi is 0. Then for pi on 3, we do the same thing. We have minus 0.9, minus 0.9, and 0. You can use your calculators for that, okay? We now move on to our curve and calibrate. Since we have to sketch from 0 to pi on 2, so we have pi on 12, pi on 6, pi on 4, pi on 3, 5 pi on 12, and pi on 2, right? So we can multiply. After we sketch this, we can now copy and paste these curves along this line. So we have the point 0, 0. The next point is pi on 12, 0.9. The next point is pi on 6, 0.9. We have pi on 4 and 0. Pi on 3 and minus 0.9. 5 pi on 12 and minus 0.9. Pi on 2 and 0. We now link these points to a smooth curve. Note that this is a sinusoidal function. So we link with this smooth curve, and this is what we have. And since this question wants us to sketch this function from 0 to pi, means that what we have here is already half of it, because this is pi on 2. So I'll just copy it again and paste. And that will give us pi on, that will give us pi, rather, that will give us pi. Now you see pi wants to sketch on the same axis a curve g of x equal to 2 plus sine 4x. If you look at this, it is just the same function that I've shifted up by 2. So we have a vertical shift of 2 units. It means that we just shift this curve above by 2 units. So we are shifting it up. When we shift it up by 2 units, this is what we are going to have. So this is the vertical shift for this function. All right, guys, hope you understood this very well. We'll take one more example, and there are numerous exercises that people can solve. For the live classes online, you can send us a WhatsApp message. Go to www.gcemathpanel.blogspot.com, and you have our contacts there. Or the easiest way is to go to GCE Math Panel Classes Online and click on the WhatsApp group and send me a comment. So example 5, we have now this function, which is a tangent function. This tangent function is divided by g of x equals tan x. Let us sketch from minus pi on 2 to 3 pi on 2. Now we know that for the tangent function, it is completely visible. You can see it clearly from minus pi on 2 to plus pi on 2, right? So let us start by looking for the period or the amplitude. Normally, the amplitude of the tangent function is infinity. That is, the tangent function has no amplitude. And the period from this function, you have just have tan x. So the period is equal to pi on 1, because the coefficient of x is 1. The period is pi. To sketch, we will just choose values of x from 0 to pi, preferably multiples in our case. Let us take 30 degrees, because since the period is pi, we take 15 degrees, we'll have so many values, and that's going to waste time. So let's take 30 degrees. If we take 60 degrees, we are going to have very few values. So 30 will be good. So we have x, 30, you have minus pi on 2. These are multiples of 30, right? So we have 90, we have 60, we have 30, we have 0, we have 30, we have 60, and we have 90. So this is from minus pi on 2 to pi on 2, or from minus 90 degrees to 90 degrees plus. So what is tan minus pi on 2? It's infinity now, negative infinity. Because sine pi on 2 is 90, cos pi on 2 is 0. So that gives us the value of what? Negative 1 divided by 0, because sine minus pi on 2 is negative 1. So you have negative 1 on 0 is negative infinity. The next one, Tan minus pi on 3 is minus 1.7. Tan minus pi on 6 is minus 0.6, approximately to 1 decimal places. Then these are the values that we have. So we can now sketch the tangent function from negative pi on 2 to pi on 2. So this is what we have. So from at negative infinity, so this is going to be an asymptotic line, because at negative, as x tends to minus pi on 2, f of x tends to negative infinity. So this value of x equals minus pi on 2 is an asymptote, the same as pi on 2 is another asymptote. So let us start sketching from these other values, and then we should indicate the asymptotes shortly. So we have minus pi on 3 and minus 1.7. We have minus pi on 6 and minus 0.6. We have 0 and 0, pi on 6 and 0.6, pi on 3 and 1.7. So at these other points now, as you have said, this minus infinity, negative infinity here, value that we have, is because x equals minus pi on 2 is an asymptote, a vertical asymptote. So the curve approaches the line but does not touch the line. Equally, at positive infinity, approaches the line but does not touch the line. So we have two asymptotic values, as you can see, and we can now link our curve like this. Then they want us, but this curve has ranged from minus pi on 2 to pi on 2. But they wanted us to sketch from minus pi on 2 to 3 pi on 2. So we still need 1 pi on the right-hand side to make it to be 3 pi on 2. So that 3 pi on 2 is 1.5 pi. We are still at half here. And this is pi. So this will be 1.5 pi around this point, somewhere here. So we copy this curve and paste again. That's at 3 pi on 2. Okay, so the asymptotes here are, you have x equals minus pi on 2 and x equals pi on 2. Thank you guys so much, and you can take these exercises. Don't forget to leave your comments and to share with your friends, to subscribe, get our blog for this note. The next lesson is on limit and continuity. We equally discuss discontinuity, and that will be followed by differential calculus 1. Thank you, bye-bye. Who is there?